Hello everyone, welcome to this series video, how can we implement the process model in PLC. In this video, I'd like to discuss how can we determine a second order transfer function. Specifically, I will discuss how can we identify an underdamped second order transfer function. That means the damping ratio between the 0 to 1. And from the previous videos, I discussed how can we identify a first order transfer function, and we can use the bump test and record the step response curve, and we can record the time, and using this time constant, and we can calculate this exponential frequency value, and then we can get this first order transfer function. Basically, the first order transfer function is simple to get there. However, while using the first order transfer function, your response curve has to follow this exponential shape. In the real industry system, not every system can react at this exponential shape. Especially some cases, you will see the system can react as this shape. If your system bump test response shows this overshoot behavior like this, and your system is single input and a single output system, then basically you could use the second order underdamped this model to represent your system. In this video, I will show how can we use this bump test curve, response curve, and we can write down some important values according to this curve, and then using those values, we can calculate those important parameters from this second order transfer function. Okay? And while we are talking about the second order transfer function, actually the second order transfer function has three types. While the damping ratio between the 0 to 1, this is the underdamped system. This is the case we will discuss. It also have two another typical style. One is critical damped. That means this damping ratio equal to 1. And when the damping ratio greater than 1, that means the system response will show very slow. We can call this second order transfer function, this is the overdamped system. Typically, if you cascade two first order systems together and their pole has a slightly different, then you will get one overdamped system. That typical style, you are using two low pass filter, cascade them together. So you can imagine your system reaction will show very slow. But in the real case, your system will react faster and your system will show the overshoot style. This is the underdamped system. And you will see there are a lot of systems will react like this way. And a typical underdamped system, we will see the right side. And our car has a suspension for each wheel. It consists with a spring and one damper here. So this is the one typical system can react as the underdamped second order system. And this is the typical second order transfer function. And keep in mind, your second order system will also have one ratio again here. This is theta named damping ratio. And this ohmic here that named natural frequency. And its unit is rate per second, RAD per second. Alright, similar idea as the first order transfer function. I will use the bump test time response. And this response will show the overshoot. I will use the overshoot, this time response curve, to record some data. And using those data, we can calculate those important values, especially for the damping ratio and the natural frequency. Okay? And firstly, we can use the Matlab. We can create one second order underdamped transfer function. We can create a time response, a bump test response. And using the curve, we can determine this second order transfer function. All right, in this case, I will use this transfer function. This is one underdamped second order transfer function, S plus 2S plus 9. And the K is equal to 5. Okay? So where K is equal to 5 and the ohmic square is equal to 9. So ohmic is a 3. This natural frequency is a 3 rate per second. Okay? And I will use this second order transfer function as an example. And let's firstly create this second order underdamped transfer function in the Matlab. And we can call this system second order system. And it's equal to the k equal to 5, right? And the transfer function inside the denominator is 9. And the denominator 1, 2, and 9. So let's see. This is my second order transfer function. Okay, we will see the denominator equal to 45 and the denominator, they are the same. Okay, this is my second order underdamped transfer function. And then we can use the step response. And let's see. This is this second order underdamped transfer function time response, bump test response. And in the real case, you can use your PLC or any controller, and you can give your system an output and record the response of your system, your controlled object system. And if your controlled object system shows like this, it has overshoot. If you recall, the first order system will show the exponential curve, but the second order system underdamped, it will show this overshoot behavior. And if you see the system will react like this, then that means basically we can use the second order transfer function to identify your system. Okay, then we will use some knowledge from the second order underdamped system to estimate your transfer function. This will need the knowledge from your control theory book. Firstly, there are a couple important words from this bump test response. So the rising time, TR. The rising time, TR, basically, let's see if this is the full response. So this is the different change of the output from here to here. Okay, maybe your system has an initial status, but this is the difference of the change. Okay, and from the difference of the change, 0.1, the 10% to the 90%, this area, how much time it used. This is the TR. TR, this is the time required from the 0.1 to the 0.9 of the entire change. Okay, and from the beginning, initial status to the peak time here, this we called peak time, TP. Okay, this is the time required to reach the first or the maximum peak at this area. Typically, in the real practice field, I would say the TP is easy to get there because from the initial status, get this maximum, the first time maximum. So it's easy to calculate the TP time. And from the mathematical wise, the TP equal to this equation. And we can see it includes this natural frequency and this damping ratio. Okay, then there's another important value. This is the percent overshoot. The percent overshoot equal to this area, this overshoot area over derive the change of the output. Okay, so you can see this definition. This is static state. Okay, this is the steady state, the difference of the y, the output value. This is the overshoot area. Using the overshoot area, derive this area. Okay, we got this overshoot. And overshoot usually comes with the percent. And finally, another important, this is the setting time, the TS here. Take care here, in this picture, is using the TS. And when the system reached the 98% of the setting status within the plus and minus 2% of the steady state value, then we will see the system got this settling status. We can write down the time. In the real practice field, since the system always comes with a noise, sometimes it's hard to calculate the TS. Typically, using the curve to determine the second order system by using those measurement time and value. Typically, we will use the TP and the overshoot. Got those two important values, then we can get this damping ratio and the natural frequency. For example, here, you will see the overshoot comes from this equation, but reversely, if we have this overshoot value, then using this overshoot value, we can calculate this damping ratio. And once we have the damping ratio and we have the TP, then we can get this natural frequency value, right? So basically, we can use the overshoot and the TP. We can have this second order transfer function. Okay, let me use the bump test from this Matlab time response. And let me demonstrate how can we get this TP and overshoot. Okay, as I introduced, the peak time and this overshoot is very important. Basically, a very important point it is here. The first time the system got this peak time here. So we can find the maximum value. So we can see this amplitude, find out the maximum value of the amplitude. When it got this maximum value 6.65, then the time it used 1.11. Okay, so according to these equations, let me show how can we calculate this. And I will use another slide. All right, according to this time response, here I will write down the TP is equal to 1.11 second. And the OS percent is equal to this area over this. Okay, so this area equal to what? This area equal to 60.64 minus 5. Okay, so it is minus 5. And the denominator is this area, so it's equal to 5 here. So it's 5. Then this is the 1.64 over 5. This is equal to, so 0.32. Okay, that means 32.8%. This is 0.328. 32.8%. This is the overshoot. Okay, overshoot value we calculated, and the TP peak time we measured. And according to this equation here, so we can use this equation to calculate this damping ratio. And this is the line. And in the Matlab, we can use this log instruction. And let me show how can we calculate this equation. And this area looks a little bit confused. Actually, this area equal to the 32.8% over 100. So it's equal to this, This is a purely value of the overshoot, 0.328. Okay, let me use the Matlab to calculate. That's because this equation is complicated. All right, here the damping ratio equal to, so the denominator, it is minus line 0.328. Okay, and the denominator, it comes from a square, SQRT square, and the pi 3.14 multiply 3.14 and plus, and then this area, and this area it is log 0.328 and multiply, this is square, right? So we'll multiply 2 times. Okay, so we will see this damping ratio equal to 0.3346. Okay, we can write down here this damping ratio equal to 0.3346. Okay, this is the damping ratio. Okay, then according to this equation here, we have the damping ratio, and the TP, we have the 1.11 second of the TP. It is here. Then we can calculate this frequency. Okay, then same thing, I can use the Matlab to calculate this. We can call this, okay, this is the natural frequency. Natural frequency equal to pi derive the TP equal to 1.11, right? And times, we'll add a bracket here, SQRT square root, and inside this SQRT, this square root, damping ratio, so and the damping ratio power 2. Okay, so we will see the natural frequency equal to 3.0018. So we will get rid of this small value. So basically the natural frequency equal to 3. So we can write down here. So according to this calculation, the natural frequency equal to 3. The unit, this is the rate per second. Okay, as we can see, once we got this damping ratio and the natural frequency, so basically this area, we can get this second order transfer function. And one important, this is the gain. How can we calculate the gain? Okay, then if we go back to this picture, we will see the steady state value, this is the 5, this 5. And this is the step response. That means the delta of the input is 1. And the delta of the output, it is 5, right? So the Ka, the gain, is equal to the delta of the output derive the delta of the input. So that means the Ka, it is 5. Then that means according to those calculations, we will see this entire transfer function is equal to omega n is a 3 square as 3 square at the denominator, and s square plus 2 multiply the damping ratio 0.3346 and multiply the frequency, and this is s plus the omega square, this is 3 square. Okay, this is the denominator, and then multiply the Ka equal to 5. Then we'll see this area equal to 2. Then this transfer function, eventually it got this. So the denominator area, this is 9 multiply 5 is a 45. And the denominator is equal to 2s plus 9. Okay, this is our second order underdamped transfer function. And then if we compare with the Matlab, so we can see exactly the same. So denominator is a 45 and the natural frequency equal to 3. So this area here, it is 9. It is 9. Here, it is 9. Okay, so this is how can we use the time response using the overshoot and the peak time to calculate the two important parameters, damping ratio and the natural frequency. And if you recall, we also have the TS here. So I would recommend using this TS, the settling time, to verify again if this damping ratio and the natural frequency we calculated correctly or not. For example, in this case, this TS denominator is 4 and damping ratio is 0.3346. Okay, and multiply 3 equal to, using 4, derive the damping ratio multiply the natural frequency, and we can see the TS equal to the 4 seconds. We can see is almost equal to the 4 seconds. So the result we calculate is a 4 seconds. Then we can verify. That means the 4 seconds is as here, right? So we will see when the system got this 4 seconds here. So basically the system is within the 98% of this reaction. After 4 seconds, basically this reaction got this 98% of this steady state. Okay, if you recall the definition of this settling time here, it got this plus and minus 2% of this steady state value here. Okay, so we will see after this verification, we will see 4 seconds makes sense. Okay, got here. That means the damping ratio and the natural frequency we calculated, basically they are correct. All right, this is the typical way to determine underdamped second order transfer function to determine the damping ratio, natural frequency, and the Ka here. Ka, this is the calculation method. And from this curve, we can write down, we can record the TP, the peak time, and the overshoot. Keep in mind, the overshoot is equal to this area over this area. Okay? This area actually is a direct calculated value from this overshoot, this calculation, 0.328 value, this area. And then using the Matlab, and while we are calculating this damping ratio is here, the denominator is minus this line log 0.328. And this is denominator. Then we calculate this damping ratio. And then using the damping ratio and the TP time, this equation here, we calculate this natural frequency. Okay, natural frequency. Then we will get this second order transfer function. Okay, eventually got here. So we verify they are the same. It is the same. Originally, we assume we have this second order transfer function here. They are the same. That means the method using here, it is correct. All right, this is the method. How can we determine an underdamped second order transfer function? Once we identify this transfer function, then next video I will show how can we do the Z transform. But I will show another method. If you recall, while we are talking about the Z transform, we derived that Z transform. So if you recall, I derived this equation, involved the zero order sample holder, this equation, and I derived this transform equation. But this derived is a little bit complicated. Then some people will ask, is there some common way or easier way, especially in the engineering world, convert a S domain transfer function into Z domain? The answer is yes. So in the next video, I will introduce the Tustin bilinear transform. This is another way to do the Z transform. So I will use the second order, the transfer function we got in this video, convert it into the Z domain transform, and eventually got a difference equation for this second order transfer function. Okay, see you in next video. Thank you for watching. If you like this video, please give me a thumb up. If you like to watch more videos in my channel, please subscribe and hit the bell. Thank you for watching.